5.4, the fundamental theorem of calculus. So we're gonna eventually get to that, but before we do, we're going to talk about average value first and how to find that, and we're going to do that by the mean value theorem. So theorem. So this is the mean value theorem. The mean value theorem. So usually the theorems they name are important, and they're used all over the place. So this is for definite intervals. So if f is continuous on a closed interval from a to b, then there exists a point x equals c that's inside this interval, a to b, such that f of c is equal to 1 all over b minus a times the integral from a to b of f of x dx. And also we can think of f of c as the average value of f. And the average value of f is equal to that f valued at c. So just another way of doing average value. And we've actually kind of discussed this before. So when we want to talk about the average value of a function, is if I had a function that was from, say, it looked like this. So this is going to go from a to b, so it's continuous on this closed interval. And I know I can find the area from a to b, and that area is the definite integral. So this area under the curve is the integral from a to b of f of x dx. Now, this is a, this is b. Now what this says is there exists a c inside here, so there's some x is equal to c, let's call it right here. And this point right here is going to be equal to f of c. So f of c is equal to this area. Now what is, how to kind of prove that this is the case is, my claim is that the rectangle created by f evaluated at c, this rectangle right here, that area is easy to calculate because it's a rectangle. So the blue area would be equal to, it'd be b minus a, because it's the width of this rectangle here, b minus a, multiplied by f of c. And that would be equal to, that integral would be equal to the integral from a to b of f of x dx. So when you solve for f of c, you get this equation. And what we also discussed this in the very first section, is if this rectangle shares that same area, then this f of c is actually equal to the average value. This is the average value of f. It's the average of f. That's weird. Well, we're going to do it anyway, but we're going to do it using the previous problem, and then we'll get to where this comes from. All right, so example, determine the average value of f of x, which is equal to 4 minus x on the interval from 0 to 3. And determine the value at which this happens. Determine okay. So what we're going to do is we're going to answer the first question first. So what I know is I know that the average value of f, I don't know if I want to leave the g in there. Let's see. I'll just leave the g out. So we'll just call AV of f. The average value of f is equal to, sometimes I see the g, sometimes I don't, but we'll leave it off because I don't think the book has it on there. So the average value of f is equal to, well, it's the area of the curve divided by b minus a. So this is b divided by b minus a. So this is the area of the curve divided by b minus a, just like we did in 5.1. Now we know a little bit more about the area of the curve is that the area of the curve is the definite interval. So what I'm writing right here from 0 to 3 is the definite interval. So man, let me do this. Let me erase this. So this would be of just writing this function in here, and then I should fill in the blanks last. So that's the average value. So what I know is that b is 3, a is 0. A is 0, b is 3. And my function is equal to 4 minus x dx. So I should have filled that in for last. So this is going to be equal to 1/3, and I know how to find these values. What I know is, remember for a constant, it is 4 times b minus 0. So this is going to be 4 times 3 minus 0, and then minus, we know how to find this as well. This is, remember, that x squared over 2. So this is 3 squared over 2 minus 0 squared over 2. So what I get is I get 1/3 times 4 times 3 minus 3 squared over 2. I was going to cheat a little bit, but I'm not. I don't want to factor things out. Minus, let's do it this way. Like they all have a 3, and I was going to cancel a 3, but I don't want to confuse you guys. So minus 9 over 2. So I think I'm going to do that for simplicity. So 12 divided by 3 is 4. So sending this in, 9 divided by 3 would be minus 3 over 2. So this is going to be equal to 8 over 2 minus 3 over 2, which is equal to 5 over 2. All right, now answer the x part. I'm going to find c now. So in order to find c, what I need to know is when f of x is equal to this value, it's going to tell me what c is. So when is f of x equal to the average of f? The average of f. So when is 4 minus x equal to 5 halves? So, well, it's linear. Just multiply everything by 2. 2 minus 2x is equal to 5. Subtracting 8 minus 2x is equal to minus 3. So x is equal to 3 over 2. Now, notice that this c value is always going to be inside of our interval. Notice that 3 over 2 is an element inside 0 to 3 because it's 1.5. Now it's not always the middle value, it just happens to be the middle value. And the reason why it is the middle value is because this function is linear. So it's kind of neat is if you want to know the average value, like here's a linear function, right? If you want to find the average between here and here, well it's going to be right there, and it's going to happen right in its middle. So since the function is linear, that's why this ended up being the right in the center. But most functions aren't linear, so we're not going to expect that. All right, so we're going to do two fundamental theorems of calculus, Theorem 1 and Theorem 2. So this is going to be part 1. So what I like about part 1 is it kind of shows the inverse properties of derivatives and integrals. They're not exactly inverses, but they're pretty darn close. So if f is continuous, on a closed interval, the reason why they do that is because it has to be integral. Its integral must exist. Then we'd say capital F of x is equal to the antiderivative from a to x of little f of x dx. And basically what we're saying is that capital F is the antiderivative of f. That's all that says. And we've already kind of defined that. And we'll explain why that's the case soon enough, but we need part 2 to really prove that. So, but this is the antiderivative. And is continuous. It's continuous on that same interval, on a to b. And differentiable on the open. And its derivative is f of x. Oh, I got something wrong here. This is wrong. It's my fault. We'll talk about it. This is f of t dt. There we go. It's better. Okay, so let me show you the formula because this is this in words. So what they're saying is that it's the derivative that the derivative of this capital F. They're saying the derivative of this capital F the derivative of capital F is equal to little f of x. So they're saying f prime, capital F prime of x, which represents the derivative with respect to x of f of x, that capital F of x. So this would be equal to the derivative with respect to x of the integral from a to x of f of t dt, which is equal to little f of x. So what they're saying is the derivative of the antiderivative is equal to the function. So really what we're showing is that that if I have a little f of x, let's do it the other way. If I have capital F of x here and little f of x here, this way is the derivative with respect to x, and this way is the antiderivative. So this is, I guess, the integral dx. Is kind of what there is what we're showing here. But I'm just gonna say, yeah, I'm just gonna put this here is gonna be the integral. I'm only gonna write that sign, even though I'm not gonna, because it's supposed to be with respect to t. So a to t dt. So this is going to be f. So the derivative of this gives us this. The antiderivative gives us this. So it's supposed to show us these inverse properties. Now, yep, okay, I can live with that. This down here is messy. I'm not extremely pleased with the writing, but it's fine. All right, so example. Applying. Okay, so we're going to start off basic. So the derivative with respect to x of the integral from a to x of the sine of t dt. So what we have is kind of the middle part of that expression. So if I go back to this part over here, what we're doing is we're doing this part of it. We're really kind of nailing this part of this equation. I'm sorry. So what I know is I have the derivative with respect to x of the integral, or the definite integral, of f of t dt, and this goes from a to x. So I have this part is what it's given us, and what we notice is that the derivative of the integral of f of t is just going to become f of x. So what's neat is we can see the derivative of the integral of f of t, so this is of the form the derivative with respect to x, the integral from a to x of f of t dt, we know is equal to just f of x. So this piece represents your f of t, therefore your f of x is going to be the sine of x. So what you can kind of see is the derivative and the integral essentially cancel. Like these pieces right here are kind of canceling, except they're not exactly canceling. This upper limit of integration becomes your variable. So it looks like this thing kind of goes in here. So those cancel and that goes in there.
Look at this, Daddy. Daddy, look. I cut the part off. It's perfectly.
It does. It fits good on your head. Goofball. Alright. Derivative with respect to x. The integral from 0 to x. Now a is any constant, so I'm not sure if I really defined that very well. Maybe let's go back to that picture. Let's make sure that that's done. Yeah, a is in the interval, so it represents any constant. So we're good. It's handled. So if I say a is equal to 0, it doesn't matter as long as it's in as long as it's defined in here. So this is going to be 1 over 1 plus t squared. And what I know is 1 over 1 plus t squared is defined everywhere. Yeah, it's defined everywhere because the denominator will never be equal to 0. So 0 works. It's continuous at 0, so we are good. So that means this 1 over 1 plus t squared is just going to become 1 over 1 plus x squared. I know it seems a little weird that we're just showing this, but the idea is to get this, to show these kind of inverse properties, but this function of t turns into this function of x. All right, C. Now, find, let's do a new page. C. Find dy dx if y is equal to the integral from x to 2 of 4t cosine t dt. All right, so this is kind of clever. So it's just another way of writing the exact same thing. So what I'm going to do is I'm going to find the derivative of this thing. So dy dx represents the derivative with respect to x of y. And what we know is this is the derivative with respect to x of y is equal to the integral from x to 2 of 4t cosine t dt. Now, the problem is these limits are in the wrong order. The bottom one has to be the constant and the top one has to be the variable. So what I need to do is I need to change its order. So this is going to be equal to the derivative with respect to x of, well, this is minus the integral from 2 to x of 4t cosine t dt. And what's nice about derivatives is constants can come out. So this is minus the derivative with respect to x of the integral from 2 to x of 4t cosine t dt. And now we have what we want, the derivative of the integral. But this function of t is going to turn into a function of x. So 4x cosine x, and we're done. Now one more.
Why is this so long?
So maybe two more. Let's do a d. What about the integral? What about the derivative with respect to x of the integral of minus 5 to x cubed of the what we got? Sorry, I'm brain farting. The natural log of t dt. There you go. Whatever. Okay, so what's going to happen here is we're going to take the derivative, but these things are going to cancel. But the problem is this upper limit is not just to x; it happens to be x cubed. So when you take the derivative of something, you have to take the so when you take the derivative of something, you have to take the derivative of the outside. Well, the derivative of the outside piece is going to be the derivative of let me erase this. This derivative of the outside piece is going to become the natural log of, well, it's going to become x cubed, because this is going to go in here. So when you take the derivative of this integral, that part's going to cancel. Man, that's so messy. That part's going to cancel. So the derivative of the outside part means this piece is going to go into there, so we get this. But now I still have to multiply by the derivative of what's inside. So I still have to multiply by the derivative of x cubed. So really this is, this takes the form f prime of g of t multiplied by g prime of, well, I guess I shouldn't say t, I should say x, but because that's my variable, multiplied by g prime of x. So that's what this is. This part right here represents the derivative of the outside. This part right here represents the derivative of the inside. So what we have is we have a chain rule going on here. So this is going to be equal to, well, this is the natural log of x cubed multiplied by 3x squared. And I'm going to put the 3x squared in front just to make sure that it doesn't look like it's part of the argument of the logarithm. Alright, so the same kind of idea. We know that this cosine function is going to go right here. When you take the derivative of the integral, this variable, these should say t's, not x's. So you know when you take the derivative of the integral, they're going to cancel, except this cosine is going to go in that t spot. So this is going to be equal to the tangent of the cosine of x. But now I have to multiply by the derivative of that cosine of x. So this is going to be multiplied by minus sine of x. And we're done. So that's the fundamental theorem over and over. All right, so part 2. So this part 2 is going to be what we use primarily for the rest of class. It's going to be used to calculate areas. That's why we use it so much. So if f is continuous on this closed interval from a to b, so every point on a to b, and capital F is any antiderivative. It's not very well written. Of F on that interval, then we can calculate it this way. Then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. So what we're going to notice is that we know that that capital F represents the antiderivative. So kind of some discussion on this. So we've already done in 4.8, we know the antiderivative of f of x dx is equal to capital F of x. So we've you know, the very first couple examples, they say here f of x, and they'd ask you to find capital F of x. And I said, well, I'm not going to write it this way. What I'm going to prefer to do is I'm going to write it in this notation that says find the antiderivative of this. I just like that notation a little bit better. And the reason why is because I know that notation is equal to it. So what we can see is that the definite integral right here, this definite integral, is actually related to the antiderivative, because it's essentially its antiderivative defined at its boundary points. So what's really cool about this is that that if you want to find this area under the curve is what we're representing, that this f of x right here, so this is little f, and then it's, you know, continuous from a to b. So if I want to find this area right here, in order to find that area in between, or area underneath the curve between a and b, all you have to do is find the antiderivative and only plug in the endpoints. It's just the antiderivative of b minus the antiderivative of a. So it's kind of interesting that you get the sum of all that stuff by only plugging in two numbers. It's really, really interesting. So it's kind of cool is that the summation is contained, you know, this area is contained by, you know, these boundaries a and b, and also the green function f. So in order to find everything inside, you really only have to worry about its boundaries and its antiderivative. Okay, so let's calculate it. So example, that's kind of mind-blowing. It's very interesting. If you want to find what's in the container, you study the container. Okay, so find the area of the curve. So example, determine Now what's funny is in 5.2 we had to do this with infinite rectangles, and it was you know, it was messy. It was complicated, but now we have something better. We actually have antiderivatives and we have definite integrals. So in order to find this area, so our solution here says that the area under the curve is going to be equal to the definite integral from 0 to 3 of 4 minus x dx. So remember that the area is equal to the integral from a to b of f of x dx. So just filling in the blanks should be that first. So this is from 0 to 3 of 4 minus x dx. Now we don't have to worry about all those rectangles. We can just find its antiderivative. Now we know the integral of the difference is the difference of the integral. So this is going to be equal to the integral from 0 to 3 of 4 dx minus the integral from 0 to 3 of x dx. So what it means is I have to find the antiderivative of 4. So the antiderivative of 4 is 4x. And I'm going to evaluate that from 0 to 3. And the antiderivative of x is going to be x squared over 2, and I'm going to evaluate that from 0 to 3. So this little evaluation bar is something we kind of use for derivatives when we plug it in, but I have two locations because I have a upper and a lower limit. Now, when you're finding the area, you're doing final minus initial. So you do the b first and the a next. So if you want to know like this distance, if I want to know the distance between 5 and 1, we do 5 minus 1. So that's where that's kind of coming from. So if I had 3 and 0, you're going to plug in the 3 first and plug in the 0 second. So that's why we do that. So this is going to be 4, and this is going to be 3 minus 0. 4 times 3 minus 4 times 0. And then minus what we get here is going to be 3 squared over 2 minus 0 squared over 2. Now you don't have to break this apart. From now on, I'm not going to write the integral multiple times. I'm just going to take the antiderivative of each one of these terms. So what I have is I have 12 minus 9 over 2, which is going to be equal to 24 over 2 minus 9 over 2 is going to be 15 over 2. A lot easier than rectangles. Let's do it again. Alright, so when we're finding this definite integral, the area of the curve, what I mean by that is it's going to be the curve to the x-axis. In this particular case, that's what we're talking about. So, what I know is that this is a quadratic and it opens down. So whatever it might look like, it's going to look something like, well, definitely knows it goes through 6, but it's something like, something like this. I don't think it's symmetric about the x-axis. It's not an even function, but so it's something like that. So if I want to find the area underneath this curve and bounded by the x-axis, I'm looking for this right here. So the reason why I had to put the x-axis in here is because you can take the area from any two numbers. I don't have to take these 2 points, but I picked these 2 points because it forces you to find these zeros. So I need to find those particular zeros. So what I know is those are x-intercepts. X-intercept, x-intercept. So in order to find x-intercepts, I set the function equal to 0. So 0 is equal to 6 minus x squared. So I don't like negative x squared, so I'm going to send everything to the other side, and then I'll factor it. So this is going to be x, well, to be a positive 1 has to be plus 3, and then x minus 2 is equal to 0. So I get x is equal to negative 3, and I get x is equal to positive 2. So this is negative 3, and this one's positive 2. So now I can find that integral. So that means the area, that means that red area, is going to equal the integral from, remember we have to go left to right, okay? So it's going to be minus 3 to 2. So when you do this, this is the bottom is your lower bound, which is your smaller number, and the top is your upper bound, which is your larger number. So of f of x, so 6 minus x squared. So make sure that you're taking your original function as well, the x. So, okay, let's find the antiderivative. So this is going to be 6x, that's the antiderivative of 6, minus x squared over 2, that's the antiderivative of x, minus x cubed over 3, and that's the antiderivative of x squared, and I'm going to evaluate that entire thing from minus 3 to 2. So now I got to plug things in. So what we first do is we're going to plug in the function. Remember, it's going to be the top number first, so it's going to be 6 times 2 minus 2 squared over 2 minus 2 cubed over 3. And then we're going to subtract it when I plug in the bottom number, so this is going to be 6 times minus 3 minus minus 3 squared over 2 minus minus 3 cubed over 3. And cleaning this up, we get 12 minus 4 over 2 is 2, minus 8 over 3, minus 18, minus a positive 9 over 2, so minus 9 over 2. And this is going to be a negative 27, so minus a negative 27 is going to be plus 27 over 3. And let's see. I'm just going to write them all as 6s. But you know what? Simplifying this. (10 minus 8 over 3 plus 18 plus 9 halves and minus 27 over 3. And then you guys can clean that up. I'm not going to do all that work. But what we get is 125 over 6. I'll see you. See you in the morning. All right, so I'm going to calculate this integral, and I'm going to kind of talk about the area of the curve, and then eventually I want to find the actual bounded area between the curve and the x-axis, and just to see what happens here. So remember that the definite integrals, it's supposed to give you the area. It's supposed to be the area under the curve. So when I calculate this, the integral from 0 to 2 pi of the sine of x dx, well, the antiderivative of the sine of x is going to be equal to minus the cosine of x. And then I'm going to evaluate it from 0 to 2 pi. So I'm going to plug in 2 pi first, and then I'm going to plug in 0 second. And then that negative cosine. So I know the cosine of 2 pi, this is going to be minus, well, this cosine of 2 pi is going to be equal to 1 minus, I know that the cosine of 0 is going to be 1, so this is going to be minus, remember this piece right here, the cosine of 0 is also going to be 1. So what I get is I get negative 1 plus 1, which is equal to 0. Which is strange because when you look at a sine function, you know that it's not just 0 all the time, so why am I getting a 0 output for an area? Well, what's happening here is its graph for the sine function looks like this. So we have a graph that goes from here and then to here. So this is our sine function. Let's draw that a little better. We'll see if that worked out or not. I stink at drawing on this computer. There we go. Okay, so when I calculated the area in the curve, we get 0, and the reason why is because when you calculate the area, depending if you're above the x-axis or below the x-axis, your sign actually is different. So since the function is positive here, when you calculate that sum, you're actually going to calculate that to be a positive number. And then when you calculate this one, that's going to be negative because f is negative all the time. So if I actually want the true bounded area, I need to do this. I need to do these separately. So this is 0, this is pi, and this is 2 pi. So let's find the actual bounded area. Let's find the bounded area. So what I'm looking for is I'm looking for the red and the blue. So what I'm going to have to do is I have to find the x-intercepts first, and we can. So I know that if you're looking for the x-intercepts, you know, this is when the sine of x is equal to 0. And we know that that happens when x is equal to 0 and pi and 2 pi. And that's when we have, you know, that's when the y coordinates equal to 0 from 0 to 2 pi. So in order to calculate these things, I need to take, essentially they say you can just take the absolute value of your all your pieces. So this area is going to be equal to, this bounded area is going to be equal to the absolute value from 0 to pi of the sine of x dx. And then you're going to add it to the absolute value of the integral from pi to 2 pi of the sine of x dx. Now what we know is the first part's positive, so this absolute value is going to be redundant, but you might not know what one's going to be positive, so it says just add the absolute values of between all these x-intercepts. So what we know we're going to do is we're going to have to find the antiderivative of each one of these. So this is going to be minus the cosine of x evaluated from 0 to pi, absolute value, plus the absolute value of minus the cosine of x evaluated from pi to 2 pi. Now plugging these in, he's squishing this in, but this is going to be minus the cosine of pi minus the cosine of 0. So that's the first one, all in absolute values. Plus, now the other one is going to be minus the cosine of 2 pi minus another minus the cosine of pi, absolute value. Well, the cosine of pi is equal to, so the cosine of pi, we're right here. Ooh, nice circle, huh? We're over here. So the cosine of pi is going to be, this is minus 1 comma 0, right? And then also 2 pi, which is right here. So this is going to be 1 comma 0. So, all right, so what we're going to get here is the absolute value of minus a minus 1. So minus 1 minus cosine of 0 is going to be a minus 1. Ugh. Absolute value. So what this ends up being is the absolute value of 2. You can see this is 1 plus another 1. Plus, now when I do this side, this is going to be equal to minus the cosine of 2 pi minus, oh, I already had that one. Write it in. So this is minus the cosine of 2 pi, which is going to be 1. So minus 1 minus minus 1. Is that right? Yep, so this is going to be the absolute value of negative 2. So the actual area underneath this is going to be 4 because it's 2 plus 2 is 4. So what's kind of neat here is this gives you 2 and this area gives you negative 2. So be careful, they're not related to the original numbers. Okay. All right, so I'm just going to kind of make a couple of these up. We've already done some polynomials, but we can kind of continue to do that. But let's say A. I want to find, so the integral from 1 to 3 of square root of x dx. No, we're going to go from 1 to 4. Because I like simple things. All right, so what I know of when I'm finding this is we know that this is the integral from 1 to 4 of x to the 1/2 dx. And the reason why I'm doing that is because I know I have to take its antiderivative. So the antiderivative of x to the 1/2 is you're going to add 1 to that power, so it's going to be 3/2 divided by 3/2, so x to the 3/2 divided by 3/2, and we're going to evaluate that from 1 to 4. So this is going to be 2/3 x to the 3/2 evaluated from 1 to 4. So plug it in the top first, 2/3 times 4 to the 3/2 minus 2/3 times 4 to the 1 to the 3/2. Alright, so for doing the 3/2 power, remember that the 2 is the square root and the 3 is the cube. So what I'm going to do is 4 square root gives you 2, and 2 cubed gives you 8. So this is 2/3 times 8 minus 2/3 times 1. So this is factoring out 2/3. This is 8 minus 1, so this is 7 times 2/3. Times 7, so this is 14 over 3. We've done that. We've done trig functions. Let's do all right. So first things first, I can pull out that 4. And now I know the antiderivative of 1 over 1 plus x squared is your tangent inverse. So this is 4 tangent inverse of x, evaluated from 0 to 1. So this is 4 tangent inverse of 1 minus 4 tangent inverse of 0. Tangent inverse of 1 is pi over 4. 4 times pi over 4. Tangent inverse of 0 is 0. Remember that when we're looking at the tangent function. This is root 2 over 2 comma root 2 over 2. So I know that the tangent value is 1 right here, and that's at pi over 4. So I know that the tangent of pi over 4 is equal to 1, so that the tangent inverse of 1 is equal to pi over 4. And I also know that right here, this is 1 comma 0, so the tangent's equal to 0 at 0. So that's how I got those. So this is going to be pi, and that's at pi. This is just going to be pi. Cannot be 0. Cannot be 1. Alright, this is to give you guys practice remembering what you do with antiderivatives. So you guys we found antiderivatives of everything, so just remember that. And now you know how to plug things in. So this comes down to remembering how to take antiderivatives. So what I know is there's no antiderivative rule for quotients. So you have to divide first and then take the antiderivative next. So this is x cubed over x minus 1 over x. So monomial denominators are obvious, so you just break them apart. So this is the integral from 1 to 5 of x squared minus 1 over x dx. And now I know the antiderivative of each of those. So that is equal to x cubed over 3 minus, well, 1 over x is the natural log of x. And I'm going to evaluate this from 1 to 5. So I get top first, 5 cubed over 3 minus the natural log of 5 minus, when I plug in the bottom, is going to be 1 cubed over 3 minus the natural log of 3. So these are going to be irrational numbers, so I won't be able to do much to them. So 125 over 3, which is here, minus this 1 over 3. So this is going to be 124 over 3. And I have minus the natural log of 5 minus the natural log of 3. And I can't really do much about that, can I? You could combine them, I guess, if you really wanted to. But their signs would have to be different. Let's see. So is it? I don't know. Maybe they'll do that. So minus the natural log of 5 minus the natural log of 3 would be, that would be the natural log of 1/5, because this negative 1 can go to that power, minus the natural log of 3. So this would be the natural log of divide the argument. So 1/5 divided by 3. So this would be the natural log of 1 over 15. I guess I don't know. I'm good with the original though. All right, so same kind of idea. There's no integration rule for products right now. So there's no product rule equivalent. So what I have to do with integration or antiderivatives is you have to do the operation first and integrate second. So simplify as much as possible and then take the antiderivative next. So multiplying this through, this is x cubed plus 3x squared dx. Now it's easy. So this is going to be equal to x to the 4th over 4 plus 3x cubed over 3, so at least those will cancel, evaluated from minus 2 to 0. So this is going to be equal to 0 to the 4th over 4 minus 0 cubed minus, when I plug in the bottom, is going to be minus 2 to the 4th over 4, plus, that should be plus minus 2 cubed. So that's 0. So I get minus 16 over 4, and this is going to be a minus 8. So minus 4 minus 8, so minus 4 minus minus 4 is going to be equal to 4. And that's it for that.